Hello everyone, my name is G Madhav and my bearing roll number is 23BQ 180445. Today my topic is about orbital elements in satellite communication. Orbital elements are the fundamental mathematical parameters used to describe the motion and position of a satellite in space. In satellite communication system, it is essential to know exact location of the satellite at any given of time to maintain continuous communication links. These elements provide a complete description of our orbit by defining its size, shape, orientation, and the satellite position with that orbit. Without accurate orbital elements, communication systems would fail due to improper antenna pointing and signal misalignment. Important points: define satellite orbit uniquely, use it for tracking and prediction, essential for an antenna alignment, foundation of satellite communication. Importance in satellite communication. Satellite communication requires precise positioning to maintain the stable links between the ground stations and the satellites. Orbital elements allow engineers to predict satellite visibility, calculate Doppler shift, determine signal delay, and design reliable communication systems, especially for non-geostationary satellites such as LEO systems. Orbital elements continuously change and must be updated regularly for accurate tracking. In important points, determines satellite visibility window, helps calculate Doppler frequency shift required for link budget calculations, critical for tracking moving satellites. 6 classical orbital elements. A satellite orbital in space can be completely described using 6 classical orbital elements, also known as Keplerian elements. These parameters defines the orbit size, shape, spatial orientation, and instantaneous position. Together, they provide a complete mathematical description of the satellite motions around the Earth. The 6 elements are semi-major axis, eccentricity, inclination, right ascension of ascending node, the argument of perigee, to anomaly. First, we talk about semi-major axis. The semi-major axis is half of the longest diameter of an elliptical orbit. It determines the overall size of the orbit and directly influences the orbital period. According to the Kepler's third law, the orbit period increases as the semi-major axis increases. In geostationary orbit, the semi-major axis approximately 42,164 kilometers from the Earth's center, resulting in a 24 hours orbital period. Determines the orbit size. It directly affects the orbital period. Larger axis is longer revolution time. GO is similar to 42,164 kilometers. All these are the important points from the semi-major axis. Next, eccentricity. Eccentricity defines the shape of the orbit. It measures how much the orbit deviates from a perfect circle when the value lies between the 0 and 1. The orbit becomes elliptical. Communication satellites in geostationary orbits have very small eccentricity to maintain the stable distance from Earth. When E equals to 0, it becomes a circular orbit. 0 less than E less than 1. When E is between 0 and 1, it becomes the elliptical orbit. It determines the orbit elongation. GEO satellites have eccentricity similar to 0. All these are the important points for the eccentricity. Next, inclination. Inclination is the angle between the satellite orbits planes and the Earth's equatorial plane. It determines how far north or south the satellite travels. An inclination of 0 indicates equatorial orbit, while inclination of 90 represent polar orbit. Inclination affects the ground coverage and is very important in global communication system. communications important points in this. Measured inclination is measured in degrees. When inclination is 0, it is in equatorial orbit. When inclination is 90, it is in polar orbit. It determines the latitude coverage. Next, right ascension of ascending node. It is in short form RAAN. RAAN defines the orientation of an orbital plane in direction vernal equinox to the ascending node. The ascending node is the point where the satellite crosses the equator, moving from the north to south to north. RAN is essential for defining the orbit horizontal orientation. It defines the orbital plane orientation measured from vernal equinox and specifies ascending node position important in constellation design. All these are the important points for the RAAN. Next, argument of Perigee. The argument of Perigee defines the orientation of the elliptical orbit within the orbital plane. It is the angle measured from the ascending node to the perigee, means closest point to the Earth. This parameter determines where the satellite comes closest to the Earth during its orbit. The major points in the argument of perigee is it is measured in orbital plane and it defines in perigee location and important in elliptical orbits. It is very important in elliptical orbits and it affects signal strength variation. And next, true anomaly. True anomaly represents the satellite position along the orbit at a given time and it is measured from the perigee to the satellite's current position. Unlike the other elements, true anomaly changes continuously as the satellite moves. It defines the real-time position and it is measured from perigee. It is the time-dependent parameter and it is used in tracking systems. All these are the major points about the true anomaly. Now we are talking about the orbital period. The orbital period is the time required for one complete revolution around the Earth and it depends mainly on the semi-major axis. Larger orbits results in longer periods. GEO satellites have a period exactly matching the Earth's rotation. And the formula for orbital period is T equals to 2 pi square root of a cube by mu. The major points from this orbital period is it depends on the orbit size and GEO time period equals to 24 hours and LEO is similar to 90 minutes and it is derived from the Kepler-Stokes law. When we talk about the Kepler's laws describe planetary and satellite motion and the orbits are elliptical with Earth at one focus. Equal areas are swept in equal times. Square of period proportional to the cube of semi-major axis. These laws are from the theoretical basics orbital elements. It governs the satellite motion and the basis of an orbital prediction essential for orbit calculations. All these are the Kepler's three laws helps to govern the satellite motion. And types of satellite orbits. There are different orbits are used for different communication purposes. First we have LEO low Earth orbit, MEO medium Earth orbit, GEO geostationary orbit and HEO highly elliptical orbit. Each has different orbit elements values. In important points, different altitude ranges, different latency levels used for specific applications, etc. First, when we talk about the geostationary orbit, satellites orbits at similar to 35,786 kilometers above the Earth's surface. They have zero inclination and nearly zero eccentricity. They appear stationary from the Earth and making them ideal for televisions, broadcasting, and fixed communication. And it is fixed relative to Earth, used in TV broadcasting. It has a very large coverage area and it has very high latency. All these are the main points of the geostationary orbit. Next, low Earth orbit (LEO). LEO satellites operates between 160 kilometers and 2000 kilometers altitude. They have short orbital periods and move quickly related to the Earth. They require multiple satellites in constellation from for continuous coverage. It has very low latency. It requires tracking antennas and it is used for internet connections. Now these are the main points of the LEO. A medium Earth orbit. MEO satellites operate between LEO and GEO altitudes. They are commonly used for navigation such as GPS. Their orbital period is several hours. They are used in navigation, modern latency, fewer satellites than LEO. Next is special orbit. It is known as highly elliptical orbit. HEO satellites have high eccentricity and provided extended coverage over high altitude regions. They spend more time near apogee. Means it is used for polar side of the Earth. And important points: high eccentricity, used for polar regions, and variable altitudes. So this is my topic, and thank you for